All right, welcome to This Explainer. We're unlocking something truly incredible today. For a lot of people, just hearing the phrase scientific method brings up these dreadful memories of dry academic checklists on a dusty classroom whiteboard. But actually, scratch that. It couldn't be further from the truth. Science isn't some boring list of chores. It's a dynamic, universal toolbox. It's literally the ultimate decoder ring that humanity has used for centuries to unravel the absolute wildest mysteries of the universe, from the pitch-black depths of our oceans all the way out to the far reaches of space. Okay, let's dive right into this. Here's our quick roadmap for today. We'll be covering 1. From myth to method. 2. The cycle of inquiry. 3. Mastering the variables. 4. Case studies in action. 5. Testing your knowledge. And wrapping it up with 6. A universal language. Let's get to it. Section 1. From myth to method. Moving from belief to evidence. So to really appreciate this, we have to look back at the dramatic historical shift from humans just kind of guessing at how the world works to actually systematically understanding it. For most of human history, when the ground shook, we just looked to the skies in absolute fear. We had this ancient belief system, right? The idea that phenomena like lightning or earthquakes were simply the result of some angry god, like Zeus throwing literal lightning bolts from the clouds. But then we evolved. We replaced that fear and mythology with precise observation. Just think about it. Today, we can literally map the thermal anomalies of mid-ocean ridges and subduction zones. Talk about a glow-up. The really crucial point here is how we actually made that massive leap. The word science itself actually comes from the Latin word scere, which simply means to know. And that perfectly represents our evolution as a species, moving from just relying on belief to actively demanding evidence. We stopped saying, well, the gods are angry so the earth is shaking, and we started saying, hey, let's ask questions, identify natural patterns, and actually test our predictions. We figured out that earthquakes are explained by the hard empirical evidence of tectonic plate movements. And that right there is the power of scere. Section 2. The cycle of inquiry, the engine of science. And this brilliantly illustrates that mechanical framework of how science actually operates. I want you to think of the scientific method not as some static list on a page, but as the interconnected gears of a giant engine. Every single great discovery follows this continuous cycle of inquiry. When one gear turns, it drives the next one. It's absolutely not a static, one-and-done process. It's a beautifully designed, machine-like cycle that keeps our understanding of the world constantly moving forward. Let's just briefly walk through these interconnected steps that keep this engine humming along. First up, you ask a question based on something you observed. Second, you form a hypothesis. Third, you make a prediction and test it out by conducting an experiment. Fourth, you gather and analyze your data. Fifth, you draw your conclusions based on that hard data. And finally, and this is absolutely crucial, you communicate your results. Because listen, if you don't share what you've learned, the whole cycle just stops cold. But when you do communicate, it usually sparks brand new questions for someone else, and this cycle begins all over again. Now, this feeds directly into the very core of our engine, the hypothesis. A hypothesis is not just a random guess. It's a testable prediction built on a super specific logical formula. It's the classic if-then statement. If I take this action, then I expect this measurable result. For example, let's say we want to know which candy melts fastest in the sun. Our hypothesis would be, if a chocolate bar and a gummy bear are placed in the sun, then the chocolate bar will melt faster. It's clear, it's predictive, and most importantly, it is entirely testable. Section 3. Mastering the variables, the dials and knobs of our machine. So if the scientific method is our engine, the variables are the specific dials and levers we use to actually control it. Let's break these down, starting with the independent variable, or IV. I want you to remember this simple phrase, I vary. The independent variable is the one single factor that the scientist intentionally changes or tests in an experiment. Think of it as the cause. It's the deliberate action you're taking just to see what happens. Now, if the independent variable is the cause, the dependent variable is the effect. I always like to remember DV as data or value. This is the factor that you are actively measuring or observing to gather your results. It literally depends on what you changed. So going back to our candy example, the dependent variable is the amount of time it takes for those candies to melt. That's the actual data you're collecting. And finally, we have the controlled variables, or CV. You can think of these as your constants. Controlled variables are essentially the guardrails that keep your scientific machine from breaking down. They are every single factor in the experiment that you must keep exactly the same to guarantee accurate results. Without controlled variables, your experiment falls into complete chaos and your data becomes totally meaningless.
Which perfectly brings us to the concept of a fair test. A fair test absolutely requires isolating that independent variable, meaning you're only changing one thing at a time. Imagine you're testing paper airplanes. If you change the architectural design of the plane, which is your independent variable, but then you also throw it way harder, and you do it outside in a windstorm, well, if it flies further, you have literally no idea what actually caused it. Was it the cool new design, the throwing force, the wind? A fair test means isolating the independent variable by controlling everything else. Same throwing spot, same throwing force, indoors with zero wind.
Section 4. Case Studies in Action. Real-world science. All right, we are taking these rules out of the classroom and going on a wild field trip to see how real scientists use this exact toolbox. Case study number 1, the salmon's journey. Guys, this is one of nature's greatest mysteries. Coho salmon are born in freshwater rivers, right? Then they migrate out to the vast, salty ocean where they live for years. But when it's time to lay their eggs, they somehow manage to navigate hundreds of miles back to the exact same stream where they were born. For decades, scientists were totally baffled. How on earth do they know the way? Are they using the stars, magnetic fields? Enter scientist Arthur Hausler. He hypothesized they actually use their sense of smell. And to prove it, he fired up the scientific method. He added a safe, distinctive chemical called morpholine to a tank of baby salmon, while keeping a comparison group in regular water. Years later, when those adult fish were returning from the ocean, Hassler scented specific river forks with that same morpholine, and the result? The morpholine-exposed fish returned exclusively to the chemically scented rivers. He isolated his independent variable, the chemical exposure. He measured his dependent variable, the number of returning salmon. And he controlled his variables by using the exact same species raised in the exact same lake environment. Boom, mystery solved. Okay, let's jump to a totally different scale. Case Study 2, Space Station Tomatoes. Down here on Earth, gravity pulls plant roots down into the soil. But aboard the International Space Station, there is microgravity, essentially zero gravity. There is literally no up or down. So how does a tomato plant know which way to grow its stem and which way to push its roots? This is a huge deal because if plants get confused, astronauts don't get fresh food. Well, NASA scientists tackled this by substituting gravity with light. They set up bright LEDs directly above the plants. And when we compare these two wild studies side by side, we see that the independent variable for the tomatoes was the environment, microgravity versus Earth gravity. The dependent variable they measured was the plant growth rate and the fruit yield. And the controlled variables, they ensured identical LED lighting and exact water delivery for both the space tomatoes and the control group back down on Earth. So despite the vast difference between a rushing river ecosystem and literally orbiting the planet, the structural rules of a fair test remain completely identical.
Section 5. Testing your knowledge. Let's identify the variables.
Okay, you've seen the pros do it, so now I'm challenging you to use your new toolbox in an everyday scenario. Let's say Maya wants to know if water temperature affects how fast a sugar cube dissolves. She drops the sugar cube into cold, room temperature, and hot water, using a stopwatch to record the seconds until the sugar disappears. I'll give you a second to think here. What's the independent variable? What is she actively changing? Yep, it's the water temperature. What is the dependent variable she's measuring? It's the time it takes the sugar to dissolve. And what must her controlled variables be to make it a fair test? Well, she better be using the exact same amount of water in each beaker and the exact same size sugar cubes. Let's try one more. Mark wants to figure out if listening to music while studying improves test scores. Group A studies in silence. Group B studies while listening to classical music. Both groups take the exact same test. All right, what is the independent variable here? What is Mark varying? It's the presence of music, silence versus classical. What is the dependent variable? The resulting data, which is the test scores. And as controlled variables, both groups must take the exact same test in the same lighting with the exact same amount of study time. See how this works? You can apply this logic to absolutely anything. Section 6, a universal language, shared across cultures. This is perhaps the most empowering realization of the whole explainer. This framework of logic totally transcends geographical borders and spoken languages. Think about it. Whether you're speaking English and saying fair test, speaking Spanish and saying prueba justa, or speaking Haitian Creole and saying tes kia kitab, the underlying systematic logic remains a shared, universal language. Scientists across the globe, working in completely different cultures, can collaborate seamlessly because they all rely on the exact same fundamental definitions of independent and dependent variables. It literally unites us in our pursuit of understanding the natural world.
So, as we wrap up this explainer, here is your exit ticket. Take a quick moment to log your own findings. Write down your personal definitions for science, hypothesis, and our three variables. Internalize these tools. Because now that you know exactly how the engine works, and now that you hold the keys to this universal toolbox, the only question left is, what mystery in your world are you going to investigate next? Keep questioning, keep testing, and I'll catch you next time.